starting from that textbook definition here, we go to our imaginary vessel, our little Erlenmeyer flask, with our molecules in the water phase and our molecules in the vapor phase. La 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 la, we've seen this before. Fantastic. It's a closed system. We're saying that it's at equilibrium, so equal numbers of particles are leaving the vapor phase and entering the vapor phase. Under those equilibrium conditions, is there some amount of pressure that's being exerted by this gas? Sure. Yeah. Where have you encountered that idea before? Where have you looked at vapor pressure? The what? What about water pressure? Aha, the vapor pressure, the partial pressure of water, which was really just the vapor pressure of water. So if this is all water, all H2O, at any given temperature, we know how much pressure the water vapor above that liquid is going to exert. As you raise the temperature, the equilibrium vapor pressure increases. And if we think back to Le Chatelier's yesterday, and we think back to liquid plus heat yields vapor, well, if we heat the whole thing up, so add heat, we shift equilibrium towards the vapor phase. We have more particles in vapor. We haven't changed the amount of space they have. So we've got more particles and we've got a higher temp. Of course the pressure is going to be higher. Equilibrium vapor pressure is only reliant on temperature. So it's purely a thing about temp. And if the system isn't at equilibrium, so if we're in the middle of a disruption of the system, then you can't use the equilibrium vapor pressure because then you're changing multiple factors. You're changing other stuff like the volume and things like that. So that would be this example here of shifting equilibrium towards vapor. We're going to change volume. Or not change volume, but we're going to change pressure for other reasons. Okay. When we talk about volatility in a substance, a volatile substance changes phase easily. And specifically, we typically talk about volatile liquids. Volatile liquids vaporize very easily, typically vaporize very easily at room temperature. And why would something vaporize easily? What holds all those molecules together in the liquid phase? Not just surface tension. Surface tension holds stuff at the top, but what's holding all those molecules down in the liquid phase at the simplest level? Forces of attraction. So all those little molecules are attracted to one another. If we think about water, it's got very high internal forces of attraction because remember, water's only attracted to two things in the whole world, itself, everything else. A volatile liquid has a very weak force of attraction between its molecules. So as a result, they go flying off into the vapor phase very, very easily. Things that are volatile fume off easily. They give off lots and lots of fumes. Think of something you've come in contact with that you believe to be a volatile liquid. Jot it down. Gasoline is one of the very common ones people think of. Gas fumes make a lot of people sick. Some people, especially young people, seem to like the smell of gas fumes. You outgrow that. So yeah, gasoline is one. Somebody had nail polish remover. That's another one. It tends to produce heavy fumes. A lot of paints. You know that freshly painted smell? Paint contains a lot of volatile organic compounds. So volatile organic compounds are organic chemicals, carbon-based, that produce fumes easily. So that freshly painted smell is really volatile liquid compounds escaping into the vapor phase and giving off fumes. So non-volatile compounds are just the opposite. They don't produce fumes easily. They have very strong what? Yeah, very strong internal attractive forces. They are really pretty cohesive. They stick together. They don't allow their molecules to easily vaporize. Oils are non-volatile. Which one do you think would dry up faster? Jot this down, don't yell it out. A volatile or a non-volatile liquid? So yeah, volatile liquids dry faster. How many of you suspected that that was the case? Okay. Alcohol hand sanitizer. You use it every day. Do you think that ethyl alcohol, the stuff it's made with, is volatile? Yeah, it sure is. It vaporizes easily at room temperature. A non-volatile liquid doesn't vaporize easily, doesn't dry quickly, because that's really what you're seeing when something dries. And so it tends to hold everything in the liquid phase. Questions, comments, concerns? So we're going to talk a little bit about boiling. And we talked a little bit about boiling earlier when we talked about phase changes. What was the big difference between boiling and just plain old evaporation? Do you remember? Boiling occurs above the temperature at which that liquid characteristically boils. So we've got a known temperature above which this occurs. What else is the big difference? Somebody said bubbles. There are bubbles. Okay, what else? Boiling happens inside the water column. Evaporation happens only at the surface. And, you know, we had said, well, the bubbles start at the bottom because that's where the heat is. What about the microwave? Have you ever boiled water in a microwave? You can do that. The bubbles still start inside the water column, and the heat's coming from all over the place. Why is this? Okay, so the differences that we named about boiling, it happens at a specific temperature, it happens inside the water column, all that stuff. What is boiling, really?
Evaporation.
Well, okay, it's the vaporization of water, transition to a vapor phase from within the water column under specific conditions, blah, blah, blah. Well, that's fantastic. What boiling really is, it is when the equilibrium vapor pressure, remember that pressure that a liquid in equilibrium, or a vapor in equilibrium with its liquid exerts? When equilibrium vapor pressure of the liquid equals atmospheric pressure. So, I want you to look at this line. What's special about 760 torr? It's standard pressure. It's atmospheric pressure. It's normal atmospheric pressure typically hovers right around 760 torr. So on any given day in here, it might be 759, it might be 770, but it's going to be in range of that. So you'll notice that this little yellow line that I've drawn, I'm going to go over it in sort of a pinkish color, intersects that 760 torr line at the same point where it intersects the 100 degree line. So this line is actually, or this graph is actually, if I told you that it was the equilibrium vapor pressure of a given liquid, notice that the equilibrium vapor pressure changes with temperature. Well, you already know that. You remember that from looking at partial pressures of water. The hotter that water is, the higher the equilibrium vapor pressure. So, according to this chart, at 760 torr, or I'm sorry, at 100 degrees Celsius, what's the equilibrium vapor pressure of water? 760 torr. Huh. That's weird. Two numbers that we're familiar with that seem to be special in some way line up like that. Isn't that odd?
No.
It's not? What does it mean? Before we say anything more about what it means, let's draw another imaginary. I'm gonna make up a liquid here, and I'm gonna make up some data for it, and we'll see if you can figure out what it means. So, this liquid A, mystery liquid A, has an equilibrium vapor pressure curve that meets the 760 torr line at 60 degrees Celsius. What does that tell us? What happens when the equilibrium vapor pressure of a liquid is equal to atmospheric pressure? We just said that's the point at which the liquid does what? boils. So at whatever temperature this vapor pressure line intersects normal atmospheric, what happens? It boils. So based on this chart, what's the boiling point of water? 100 Celsius. Is that correct? Yeah. Based on this chart, what's the boiling point of liquid A? 60 Celsius. Could you find the boiling point of any liquid? Yeah. Given an equilibrium vapor pressure chart, you could. Now let me ask you this question. Looking at this chart, so let's see, 760, we'll toss in some more lines here. Looking at that chart, can you explain to me why water boils at a different temperature up on Mount Everest than it does here in Ohio? Would water boil at a lower temperature or a higher temperature? Lower temperature. Why? Reduced pressure. So if the pressure on Mount Everest is 500 torr, we can figure out at what temperature water will boil by using an equilibrium vapor pressure chart. And you can look at a chart like this for any liquid vapor pair. So it's a handy little way to identify changes in boiling point. What would happen if we increase the pressure on something, like we put something in a pressure cooker? Would it boil at a higher or lower temperature? Higher. And that's exactly the principle behind a pressure cooker. So if you've ever had somebody, if you have a pressure cooker at home, it's just a heavy metal vessel with a locking lid and a seal, and when you apply heat to it, you pressurize the interior. So it allows water to boil at a higher temperature than it normally would, so you cook your food faster. Okay, so the molar heat of vaporization is just the amount of energy that it takes to convert 1 mole of a liquid into completely, every single molecule, into the gaseous phase. So it's the amount of energy that it takes to move all of these water molecules up into the gaseous phase, or any substance. So if it takes more energy to convert something from a liquid to a gas, what does that mean about its ability to cool something down? Okay, so if I have two substances, substance A, substance B, and substance A requires 10 kilojoules of energy to transform a mole of this liquid into a vapor, and substance B requires 1 kilojoule of energy to transfer 1 mole of this liquid into a vapor. And I want to use each of these as a cooling bath. So I have some small hot object here, a chunk of metal, something. I want to quench it, I want to cool it down. I want to drop it into one of these substances. Which one is going to do a more effective job cooling it? So we would probably want to drop it into A. Substances that have a high molar heat of vaporization require a lot of energy to vaporize. So this substance A is going to be able to absorb a lot more energy from that hot object before it vaporizes. It's going to require a lot more energy to raise its temperature. Water is a great cooling agent because of the fact that it's got really strong internal bonds. It's got hydrogen bonds, it's a polar molecule, so it's got the polar forces of attraction going on, dipole attractions. Water is a good coolant. Okay, so to keep exploring the concept of molar heat of vaporization, I've got 3 imaginary vessels here with 3 substances in them. I've got alcohol, like we find in hand sanitizer, like an ethyl alcohol. I've got water, and I've got oil. These are all substances you are familiar with. If I put a sample of each of the 3 of them out on a table, 10 drops of each, which one's going to dry up fastest? Okay, so would we say that it is the most volatile?
Yes.
Okay, so volatility increases, oops, that direction. So the alcohol will dry up the fastest. The water is going to dry up after that. The oil is going to take weeks or months. We're still going to have an oil slick there. Not very volatile. Very, very low volatility. In terms of molar heat of vaporization, how much energy does it take to get all of a substance to vaporize? Do you think it takes more energy or less energy to get something like alcohol to vaporize than it does water? So compare the alcohol and the water. We know that the alcohol is going to dry faster. Does it take more or less energy to vaporize the same amount of alcohol? Less. Okay. So this is going to have a lower molar heat of vaporization. The things that are very volatile, that have high volatility, have lower molar heat of vaporization, because molar heat of vaporization is just a characteristic of the material. It's not an amount of energy in the material. Does that help? So which of those three substances would you pick if you needed to use a cooling agent for something? Oil. Oil cooling. And in fact, if you look at a process where they're doing industrial drilling, very often there's a little oil squirter where they're running like a diamond drill through really heavy steels and stuff. It'll be an oil lubricated tip, and there will be oil that runs down the drill bit to cool it, because it takes a lot of energy to vaporize.
Like on a chainsaw.
Like on a chainsaw, exactly. You've got chain oil. So you've got that oil acting as a cooling agent because it can absorb a lot of heat energy before it vaporizes. Does that help? Does that make sense?